Okay. First of all, you need a sheet of paper, take out a sheet of paper, copy this down, and you'll need put it at the top of the page so you don't have the calculations below it. And I'll explain what this is going to be in just a second. So copy this down. Once you get it copied down, you need your calculator. If you have your coloring pencils, take them out. If you don't, it's fine because you're not going to turn this in. What I need is the current in the circuit. I need the voltage across each resistor. So work that out for me. Current, the voltage across each resistor. Anybody got the total resistance?
50-30.
How much?
50-30.
1530.
5030.
5030 ohms. Anybody second that? Is that what you got?
Did you forget to break down R4 into K1? Because I got 5.03.
So I got 5.3.
Because I didn't K1.
What'd you get?
5.2 kilograms, that's fine.
1K, 1.5K, 2.2K, and 0.33K. And this is right?
Yeah.
Okay. All right. What do I need next?
Current.
I need current. I got a value for current.
2.98.
That's correct.
E1 and is I times R1. Anybody got a value for that?
2.98 volts.
About V2,
4.47.
4.47. And then V3,
6.55.
and then the last one, V4.
0.9834.
All right, somebody just check for me. Add up this and this and this and this. It should add up
I
to
did,
what?
I added them up. They're
It adds to 15.
14.99.
Now, does everybody see how we got this calculation? Everybody see it? Okay. If you see it, open your lab manuals. Do you have your lab manuals with you? If you don't, I have copies on the back. Open your lab manual to page 69. You will see the lab on series circuits. So make sure that when you actually do the lab, that you read the summary of theory. Look on the next page. There's a page, I don't have the page number on my copy, but on the next page, see the box there? What does that say?
The algebraic sum of all voltage rises and drops around any single closed path in a circuit is equal to 0.
Anybody know what that is? The algebraic, what does that mean when you say the algebraic? When they say that sometimes, what does that mean? It means you take into account positive and negative signs. They're sign numbers. So the algebraic sum of voltage rises and drops around any single closed path in the circuit is equal to what? Zero. Now what does that mean? Well, what it means is that if I know the voltages, let's just put them up here. I know that this voltage right here, we'll call that V1. V1 is across this. We'll call this V2, V3, and V4. And remember what I said in class about polarity across a resistor? How do you determine the voltage polarity across a resistor? What's that? What defines it? Is it correct to think that the polarity on the left side of R1, now listen to how I say this. Is it correct to think that the polarity on the left side of R1 is positive because it's connected to the positive side of the battery?
No.
The answer is no. It has nothing to do with anything. What determines the polarity across a resistor is what? The direction of current through the resistor. So it's defined, when we're talking about conventional current, if current is traveling from left to right, and the polarity is like this. If current is traveling from right to left, and the polarity is like that. It's important that you understand that. I'm going to revisit this later on. All right? So, if my current is already here. We defined the direction already. So that means the polarity across R1 is like this. And this would be like this. And this is, you see what I'm doing? How we got those polarities? Now, in the definition there, that's a statement of Kirchhoff's voltage law. It says the algebraic sum of voltage rises and drops. What's a voltage rise? Well, the voltage rise is when, let's say we go around this path this way. If I go from a low negative to positive, that's going from a low to a high, we call that a rise. If I go from a positive to a negative, we call that a drop. So if I go this way, I'm rising, what, 15 volts, I'm going to drop V1, drop V2, drop V3, drop V4. When I get back to where I started, the sum should equal what? 0, right? So if I start out with 15, I don't have a place to write this. If I start out with 15, That's a rise. Now this would be a drop, so V1 would be minus 2.98, minus 4.47, minus 6.55, minus 0.983. All that should equal 0. What if I go the other way? Does it matter? If I go this way, counterclockwise, instead of this being a drop, it's a what? It's a rise. So this would be positive, this would be positive, this would be positive, this would be positive, but this would be what? Negative. It's the same thing. So that is just another statement of Kirchhoff's, or Kirchhoff, somebody corrected me. Somebody played their phone and the guy pronounced it Kirchhoff. But I'm going to still say Kirchhoff because I've been saying it for 20 years. So Kirchhoff's voltage law is just a statement of Kirchhoff's voltage law. Now on the next page of your book, turn to page 73. Look at table 6.2. Table 6.2 is for this circuit, but notice they have VAB, VBC, VC. You see how they have that?
Yeah.
But they also have these points in the circuit. And make sure you're clear. Make sure you understand that VAB, I'm not showing the meter there. They have an ammeter. Here's my ammeter right here. VAB is really V what? V1. You see it? VBC is V2. VCD is V3 and so forth. So in your table, we already did the values. Right here, go ahead and write that in. For current, just write it under computed values. For current, go ahead and write 2.98 milliamps. And then write VAB, VBC, VCD, put those values into your lab manual. So, we have all the values. You have those written into your lab manual. Now, turn to page 71 and read procedure 9. Read step 9 to yourself. Step 9 says, open the circuit at point B. Measure the voltage across the open circuit. Call this voltage V open. Prove that Kirchhoff's voltage law is still valid for the open circuit. Write the algebraic sum of the voltages on the third line of table 6.3. What does that mean? Well, how are we going to prove that Kirchhoff's voltage law is still valid if we open up the circuit at point B? Kirchhoff's voltage law is always valid. So let's look at what happens when we open up the circuit at point B. If I open up the circuit, now before we do that, how did you get this value for V1? You said V1 was 2.98. How did you get that value? Yeah, you took the 2.98 milliamps from here, and you multiplied it by the 1K ohm from here. And when you did the math, you got 2.98 volts, which is correct. If I come in here and I open up the circuit at point B, what's going to happen to the current?
0.
It's going to go to 0. If I put a 0 in here for V1, what happens? It goes to 0. It goes to 0. Remember in lecture and in the video lecture that we did and the face-to-face lecture we did, we said that if I take a resistor and I lay it on the table, what's the value of it? 0. Exactly the same value or voltage that you get across a piece of wire. An ideal piece of wire we call a short circuit. So basically, when I open up the circuit, no current flows through the circuit. There can be no voltage drop across a resistor. You can't have a voltage drop across 0 resistance. So in your mind, I want you to think of when you see a resistor, I don't care if it's connected to a circuit. If it's open and there's no current going through it, in your mind, just replace that with a piece of wire. If I replace each of these resistors with a piece of wire, this is a piece of wire, there's no current going through it. This is a piece of wire. This is a piece of wire. This is a piece of wire. If I do that, when I measure from here to here with a voltmeter, all I'm doing with those wires is extending the positive terminal to this point and the negative terminal to this point. This is exactly what you do in your car when you want to give somebody a jump. You take your jumper cables and hook to your battery, the good battery. You come over and you got the other end of the jumper cables in your hand. You've extended the terminals of your battery to the end of the jumper cables. So if I measure across this open, what should I measure? 15 volts. You always measure the total voltage across an open circuit. Another example of this real quick. What is a fuse? What's it used for?
Limit current.
To protect against overload of current. If you short something out, the fuse will blow and protect your circuit. So let's say I have this in my car. My car battery is 12 volts. Here's a fuse. Here's how you draw a fuse. Maybe I got some device over here, right? Often these fuses, especially if you have some that you add to a car, they're in some kind of a case and you can't actually see the fuse to see if it's blown. Let's say you couldn't see the fuse. If I have a good fuse, inside of a fuse, you ever seen a car fuse? The old kind, you have a metal cap here and a metal cap here. There's a little thin wire, a little thin filament that goes across it that completes the circuit. And when you overload the fuse, that wire will melt and it'll open up the circuit. So as long as I have a good fuse, if I take my voltmeter and I connect from one end of the fuse to the other end of the fuse, you won't read any voltage. You measure the voltage across a piece of wire. That's what's inside of there, a piece of wire. But if the fuse blows, if it opens up, then you got this situation, right? No matter what the resistance is in this box, the resistance goes to 0 when no current goes through it. So if I measure across here, across the blown fuse, what should I measure? 12 volts, just like you would measure 15 volts here. So I can test to see if the fuse is good or bad. I never have to even see the fuse if I understand the statement I just made and the logic we just presented to you. You see it? Questions? So, now the next question should be, how in the heck are we going to do lab? Is anybody taking Digital 1? Nobody's taking Digital 1. Okay, well, when you get to Digital 1, we use a simulation software called Multisim, and it's in the lab in there. But what we've done is the school, they bought a license for you guys to download this simulator. It's a circuit simulation software. And so what you're going to do is you're going to do it via remote. You can download this. I don't know how much it costs. It's expensive, but you guys get it like through June for free. Okay? So the first thing you got to do is very important. This paper right here. I didn't put holes in this? No, dude. I don't want you to lose this. I should have put holes in this, but don't lose this. So over here, what you got to have a PC or a laptop. You got to have that. If you don't, you have to come to the school to do your labs because we have the program in there. But if you have a PC or a laptop, I don't know if it works on a Mac. I don't know if you have a Mac. I don't know. You have to check. But the instructions, you go to the website here, and the instructions for downloading it to your device is right here. And then you'll need some kind of a serial number or code there on the other side. Okay, so when you go home, at some point, download the software and make sure you can get the thing to run. That's the first thing you got to do. Once you download it, I want you to go through this tutorial step by step. Now the version you're going to download is a newer version, but I'm pretty sure it should match up with this pretty well. So take your time and go through this. Since we're not meeting face-to-face for lab, you guys got to become multi-sim experts. It's actually kind of intuitive, and I think you'll probably like it. So step one, go home, download the software. Step two, when you got time before next lab, I want you to go through this. You might have to go through it a couple times to get used to where things are and how to interact with the software. Okay? Once you do that, all of the rest of the labs will be virtual. Okay? So the first virtual lab, it says lab 1 on here because when I teach digital, this is what I give them. We actually start with multi-sim. But this multi-sim lab is what I want you to do, and you will submit this to me. I don't know how we're going to submit it yet. Don't ask me that. I gotta think about that. But this is your first virtual lab you'll do. You'll go through, you'll build these circuits, and you'll see how to hook the meters up to read the values. Okay? So you'll get credit for this as a lab. So that'll be due next week. Once you do that, the following week, you're going to do the lab we just got through calculating. That's why I want you to get those numbers. So now you know what the numbers should be, and all you're going to do is build this in multi-sim and verify that the numbers should be what they should be. And in multi-sim, you should be able to open the circuit right here. In multi-sim, you should be able to put a voltage across here and prove to yourself that this voltage is 0 and that the voltage right here is 15. Prove that. Show me that you can prove that to me in multi-sim. All right? And then every week I'll go through and I'll tell you which labs. We're going to do the labs in order. We're going to skip 1 or 2 of the labs because I think it's just too hard to do in multi-sim. Now, some of the labs are going to require an explanation, and I'll do it on video. You don't have to come in. Or if you have questions, we can set up a session to where you can ask me questions. But you're going to do the labs virtually instead of face-to-face. After this week, we're not allowed to meet on campus with students for any kind of class session. I'll still be here for office hours, though, and I'll still be here. I know Felix came up the other day. I had somebody else come up. We're getting one-on-one help. We can do that. If the problems in there are too easy for you, you want something super hard. In class, we don't have time to really dig into stuff, but you know, if you want to come up one-on-one and work some more challenging problems, we can do that. I like to get stuck. I mean, I'll get stuck too and get unstuck. And it takes me time to do that. I might look at a problem for a whole hour at home before I figure it out. But I got another book in there, the one we use up at UC, that's got some really good problems that we can get stuck and find our way out of it and get the right answer. Okay? So everybody clear on the lab. I got it right here. Download multi-sim. Do the multi-sim tutorial. The multi-sim lab is that one page, and then experiment 6. So if you want to get this out the way, you can knock that out of the way too. You can do it. It's really simple once you see how multi-sim works. Questions? All right, now this other material, what is that? Well, I gave a video lecture on Thevenin's theorem. And this, if we had done that in class, I would have given you this page right here. Now notice there's nothing on this page. Did you pick it up over there? There's some pages. You didn't get it there over there. There's nothing on this page, so what I would have done is what I did in the video. I would have walked through those steps and written those steps down on this page, on this page. So you have the steps to Thevenin. Now it's in your book and it's on the video, so you don't have to worry about it. But that's what this is. And then the problems that we were doing were these. And I think I did a practice problem. I did the first problem, and then I gave you figure 2 to do. And I said when we come back and lecture, okay, when do we lecture again? What's today? On Friday, we'll pick up right here with this problem. I put this on Blackboard, but I wanted to give you a hard copy of it. So we're going to start with problem number 2 on Blackboard. Now this is going to be counted as a quiz grade right here. I want to talk about this one, and I want to talk about something that Steve mentioned. So look at this page right here. This is a series parallel problem. Let me show you how to think about this. You understand what an open circuit is? Everybody see that? Open is a break in the circuit. But there's something called a short circuit. I want to show you. I think you kind of know what it is, but I'm not sure that you know how it affects the circuit. I want to make sure you're clear on that. And you'll need that for that quiz. So let me give you a circuit. I'm going to give you two circuits. I'm going to give you this one. I'll do it like this to make it simple. I'm going to make this 10 ohms. I'm going to make all these 10 ohms to make it easy. I'm going to make this 9 volts. I'm going to give you the same circuit the other way. This is 10, this is 10, this is 10. All right, so we'll start with this. What is the voltage across in the series circuit? What's the voltage across each resistor? 9? The total is 9, so if I go from here to here is 9.
Oh.
But what's the voltage across each individual resistor?
39.
3, right? If I have 3 equal resistors across 9 volts, each one's going to get 3 volts because it's got to add up to 9, right? So I know that this is 3 volts, this is 3 volts, and this is 3 volts. So these are my voltmeters right here. 3 and 3 and 3. That's what the voltmeters read. Now, while we're looking at these 3 voltmeters, let's say somebody comes in here and takes a piece of wire and connects from here to here. What's going to happen to this voltmeter and why? Explain your reasoning when you answer. What's going to happen to that voltmeter?
0.
It's going to read 0. Why will it read 0? There's a lot of ways to think about it. Kevin said, well, current, here's what current's going to do. Remember, in order to make that 3 volts, the current had to flow through a resistance to give you that voltage drop of 3 volts. If the current doesn't flow through the resistor, it's not going to give you a voltage drop. So current's got to flow through R1, 3 volts. It's got to flow through R2, 3 volts. But what happens right here? It's going to take the path of what? These resistors and do that. No current actually goes to R3. Now we got an ideal wire here, a perfect wire with 0 resistance. So no current, it's going to bypass. A short circuit is a bypass. And because this is being bypassed, this is going to be 0. Here's another way to think about it. Can you see here I really have a parallel circuit? I got R3, which is 10 ohms, in parallel with another resistor, the wire, which is 0 ohms. 10 in parallel with 0 is what? 0. No resistance, I don't have a voltage drop. Anything in parallel with the short circuit, any resistor in parallel with the short circuit, the short's going to take that resistor completely out of the circuit. So what's going to happen if I do the short over here? Now, if I put my voltmeter across here, what would I read? 9. If I walk all the way down here, what will I read? 9, because a parallel circuit has the same voltage from one end to the other. But if I take that short circuit and put from here to here, what will current do? Current's going to leave here and do what?
All the way down.
All the way around like this. No current's going to go through any of those branches. Why? Because current takes the path of switch resistance. Well, if there's no current going through there, there can't be any voltage across it. So if I put my voltmeter across here, what will I read? 0. That's That's if you can do it before the battery blows up and the acid gets on you and you're fried to death. Well, I don't want to say that. I get in trouble when I say too much. You see it? So basically, a short circuit will change the circuit. You got to look for that. So in this circuit where I shorted this out, that 3 volts is gone, which means that each of these now has what? This will go to 0. This will change to what? 4.5. 4.5, because that 9 volts still got to do something. Does that make sense? So now, what do you have here? Ooh, boy, look at that. How are we going to do that? You got to go home, and this, I'm going to give you a little while to think about this. I'm going to count this as a quiz. Keep in mind this idea of a short and an open, and then I want you to try to solve for the voltage across each resistor and the current through each resistor for both circuits. All right? And keep this in mind. We talked about short circuits. Okay? And then the final thing, and don't forget, don't leave when I'm done because I want to go. I got to make one more lab for you. I forgot. And everybody needs this. So Steve asked a question about the lecture. We talked about the input resistance and the output resistance in the lecture when we talked about Thevenin's theorem. And let me say a little bit about that. In a lab situation like this, all we do is come in here, we get the breadboards, we hook up circuits, usually resistors, eventually capacitors and inductors in this class. We take some measurements. But devices, your cell phone, calculator, any electrical device, these components that we're looking at in the lab, any electrical device will have these components in it. So even though we're just practicing laws and verifying things in lab, when you get out of here, you're either going to be testing, fixing, or designing things based on these components. So even though we're dealing with circuits, in the real world, you deal with devices, electrical devices. And what I tried to get across to you was any kind of electrical device is going to have an input and an output. The input is where you put power in. The output is where you get some kind of energy, power, some kind of work out. An example I used in the video was your cell phone charger, but let me use an amplifier. Now, an amplifier is a little different because it has more than one input. An amplifier has a DC input and it has an AC input. The DC input, if you ever installed an amplifier, that's the red, the black wire you hook to your car battery. The AC input that's what you amplify. That's the audio that you amplify. But let me just do this. Let me just call it a device. I'll make it more general. So here's a device, and whatever this thing is, a widget, whatever you want to call it, it's going to have a power wire over here that you hook up. And if there's something, let's say this is your cell phone charger, you hook this to power, and your cell phone will go here, and you plug it in some kind of way. So this represents a connection of something. So the way I represented that with a resistor called RL, where the L stands for what? Load. So if this is your cell phone charger, your load will be the phone. If this is your amplifier, the load would be a speaker. If this is whatever device this is, if there's something that you hook to it, we call that the load. Over here, we got to hook up the power, and for us in here, it's going to be a DC, because that's what we do. We do DC in this class. So you might have a battery here powering this, and over here, here's the load. Now, you know Superman, one of his powers is his vision. What's special about his vision? Yeah, he has X-ray vision. You guys know that? You know your superhero. That's part of the exam, by the way. He has X-ray vision. He can't see through, though. He can't see through lead?
Yeah, it's lead.
Yeah. Okay, I think he can't see through. Well, let's say we have a metal case here, and we got our X-ray vision on, and we look inside of here, and what we see is a bunch of stuff in here, but this is a really simple device. All we see is this. We see a resistor, and we see another resistor. There's a circuit. Now, in any device, you're going to have way more stuff than that. You're going to have transistors, and you have a bunch of stuff that we'll talk about as you go through your degree program. But this one just has two resistors. It has a 6 ohm, and it has a 3 ohm. And maybe this is 9 volts. If I say to you, Kevin, I want to know the resistance of this device. So Kevin will say, well, okay, Ron, you want to know the resistance of the device. First thing I got to do is take this battery off. And I'm going to take my meter and hook it up here and put it on ohms. Well, that would be the wrong way to do it. Because what I asked Kevin for was the resistance of the device, not the device and the load. I just want the device. So what you got to do is you got to take the load off. You got to unplug the cell phone and now put the ohm meter here. And you will see that that's a series circuit. Because current's going to come through here. If you disconnect that, it's now a series circuit. Current's going to come through here, and what you're going to measure is what? 9 ohms. Well, that's what we call the input resistance. Now, we've been talking about this all semester. We've been calling it the total resistance, the Thevenin resistance. When you get your job and you go work for GE or P&G or whatever 2-letter company you go work for, the 2-letter companies pay you more. Whatever one you go work for, you'll never ever hear total resistance. You'll never ever hear equivalent resistance. You will hear input resistance or impedance. That's what they call it. So what the input resistance is the resistance from the point of view of what? The battery, the power device. That's what we've been talking about all semester. Input resistance. We've just been calling it something else. The new stuff is, with Thevenin's theorem, Thevenin says, okay, well, not only do we have values for current, voltage, resistance from the point of view of the power source, we also have a voltage and resistance from the point of view of what? The load. See, if the battery had an eyeball and could see in there, it would see a resistance of 9 ohms. But you can ask the same question for the cell phone or the speaker or whatever your load is. What does it see looking back in there? What does it see? And what it sees is, what I showed you in the video, it sees the Thevenin circuit. It sees the Thevenin circuit. It sees VTH for voltage. It doesn't know anything about the 9 volts. It sees VTH. It sees RTH for resistance. It doesn't know anything about a 3 ohm and a 6 ohm in series. It don't even see a series circuit. Okay, Kevin, I want you to measure the resistance from the point of view of the load. Well, again, I got to take the battery off. But when you measure resistance from the point of view of the load, you really don't take the battery out or the power source out. What you do is you set it to 0. Well, how do I set it to 0? If I take a battery, it's 9 volts, and I put my voltmeter across that battery, from there to there, that voltmeter is going to read 9 volts. While that voltmeter is connected up and you're looking at it reading 9 volts, if somebody comes in here and connects a wire to it, guess what's going to happen to that? It's going to read 0 because that's a short. And right after it reads 0, it's going to blow up and you're going to get burned to death. I got to quit saying that. It's not a good idea to short out a big battery like that. But that's the way you take it out of the circuit. So Kevin's going to say, all right, Ron, if you want me to measure the resistance this way, then I got to set the voltage source to 0. The way I do it is where's my eraser? I take it out of the circuit and I replace it with a what? Short. Now look at this. This resistor and this resistor are already connected together on the top like that. I got a 3 ohm and I got a 6 ohm. As soon as I do this, I'm taking the wire and connected this end to this end. What kind of circuit is that now? Parallel. And if you take 3 ohm and parallel with 6 ohms, by now you should know it's what? 2. 2. Well, hold on a second, Singleton. Are you saying that the voltage source sees one resistance and one voltage, and the load sees another one? That's exactly what we're saying. This Thevenin resistance This resistance that the load sees, you call that the output resistance. That's R out. In a textbook, they ain't gonna call it that. In a textbook, they're gonna call it the Thevenin resistance. But when you go work for P&G, when you go out and work and do this stuff in practice, you'll never ever hear the word Thevenin. You'll hear the output resistance or impedance. Impedance is an AC thing. You'll get to that. You see it? What's important though is that next thing that I talked about in the video, maximum power transfer. If you want maximum, sometimes you don't really care about power. If you don't really care about power, you can stop right here. But if your design, your circuit, you want maximum efficiency, maximum power, with an amplifier, that's what you want. If I have a 100-watt amplifier and I hook up a speaker for the load, I want as much of that 100 watts to come over here as I can get. Most of the time, you want maximum power, maximum energy to the load. That's only going to happen when what? When this resistance and this resistance are what? Are the same. When RL is equal to RTH. Well, can you prove that, Singleton? Well, you already proved it. Didn't you do the power lab? Remember the last lab you did? Did you notice that last lab you did looked a lot like a Thevenin circuit? Did you notice that? In that last lab, here's what you had. Let me remind you, and then we'll go. In the last lab, what you had, I think it was 15 volts. It might have been 12. I think you had a 15-volt battery or something like that. And then you had a 2.7 K ohm resistor. But this over here, I'll call it RL. What that was a potentiometer. And they said, all right, I want you to hook it up as a rheostat. So you did that. And then what they said, I want you to turn the potentiometer and watch what happens to the power. And what you didn't know this then, but what you noticed, some people said it to me. They said, I think I did something wrong because my numbers started going up and then they started to go back down. That was weird. What you didn't know though was this thing about maximum power. What you were doing as the resistance of this approached this, resistance of R2 approached that resistance, and this is power for R2. Let's say right here was when R1 and R2 were equal, then what you should have seen was the graph is going to do this. It's going to peak right there, and then it's going to go like that. That's why I asked to see your numbers. I can just look at the table and say, yep, you're going to get a good graph. Now, I'm a big fan of this maximum power stuff. Well, back in my younger days, I was in my 20s. You're 19, Felix? You're 19. I was like 21 or 22. I had a business, me and a buddy called Cincinnati Car Alarm, and we hooked up alarm systems and audio and all of that. And I always wondered, why they got every amplifier hookup had 2 ohms right there. It had a metal plate for 2, and I said, well, I know we're supposed to hook up a 2 ohm speaker. Why? Why is it 2? Well, what it is they're trying to put out this thing for maximum power transfer. A 2 ohm speaker and all the other crap in there has some kind of 2 ohm equivalent. If I want my 400 watts to get to my speaker, if I have a 100-watt amplifier, I got to make those match. And I'll go into this in a lot of detail if you take me for AC. This is good. It's good AC stuff. Now, if you take the other guy, I don't know what you're going to get. So you got to take me for AC. Okay. Anyone have any questions? Well, I think that's it. So let me stop the recording, and you guys just chill for 1 second and let